Let me start with a question about composite electroless nickel. It's something that my company's been involved with literally since the 1970s. And my father was, one of the real pioneers in that technology going back that many decades. How many people have seen it? How many people here have seen, one or more versions of composite electroless nickel? How many are? It's a good amount, but still some good opportunity for more people to be involved in this technology. How many people are in shops that are actually producing one or more forms of composite EN? Okay, also room for growth, but that's good. I'm glad that people are here and look forward to hearing about your experiences. So for those people that are not as experienced with it, I'll explain what it is. I'll go through the various types. On some, I'll focus more on the coatings. On other, I'll focus more on how the process is done. Brad is also going to hand out some samples just to pass through, because pictures are worth 1,000 words, but to touch and feel the different versions. And I'll explain what they are. I think gives you a really good sense of what they are. They're on Q panels. I think our industry single-handedly keeps that Q company afloat, but obviously these coatings can go onto anything electroless nickel can go onto, so very complicated geometries. But hopefully touching and feeling those will be useful to you. The picture on the screen is a typical cross-section picture. In that case, it's diamond within electroless nickel. That's about 40% diamond, 2-micron size. I'll explain the use of that one in particular. But in general, it's just any type of fine particle within electroless nickel is a composite EN coating. There's different words, composite, co-deposit, but I just typically use the word composite. And it's essentially the same process of electroless nickel. This generally the same fixturing, the same pre-treatment. You're putting it into a hot electroless nickel bath for a period of time. Masking can all be done the same. You're taking it out, rinsing, drying, unmasking if necessary, and heat treatment. So it's a very, very similar process to what everyone here is familiar with the addition of particles to the bath itself. And I'll explain how that's done and some modifications that need to be done to the bath and fixturing to make that work. But it's something that has been done for decades. It's in tanks as big as 4,000 gallons being, put onto, massive pieces of equipment and tiny things that go inside the body both. So it's very versatile. These are the most common types of composite electroless nickel in the world today that are in use, not in any particular order. But those are the most common types that are being used. But I'm going to actually preface that with two types that we've developed over the years that are not really in use, but to give you an idea of the versatility. One composite that we've created, and it was with a university, a medical school, was electroless nickel with bone fragments inside. And it was for bone, like hip transplants and things, so that the bone could then grow on top of other bone, and it actually proved to work very well. A great paper was written about it. But again, just to show, you can put essentially any particle into electroless nickel. After 9/11, we actually developed a series of coatings that used a type of material called intumescent materials, things that under high heat form a char. And if anybody remembers, one of the tragedies from that day is that insulation material that was on the beams of the World Trade Centers blew off very fastly. It was sprayed on to the structural supports of the buildings, and we found that if we put intumescent particles into electroless nickel and then was plated onto the beams, you can then spray another material on top. It bonded better and provided longer protection, and that can be for structural beams, but even in hallways of stairwells in buildings and elevator components, things that can then last longer under fire. I'm not here to promote those. I'm just using those as examples of how creative you can be putting fine particles into electroless nickel to get the benefits that we know, the hardness, the corrosion resistance, adhesion to base metal, perfect conformity, as well as whatever the properties of the particles may be. So let me go through the main types that are in use one by one, starting with wear resistance. And I've got some charts and pictures here that I'll explain. First, let me start with the photographs. What you see are two different versions. The top photo is Electroless nickel with silicon carbide. I think you can notice it's a very different shaped particle than the diamond in the photograph below. It's just the nature of the material. Both particles are useful in different industries and different applications. Typically, with the diamond, for hardness and wear resistance, the particle size is between 1 and 10 microns. In this case, it's 2 microns. And when I say between 1 and 10, I don't mean that a coating is going to have some 1 micron and some 10 micron and some 8 and all over the map. No, it's very, very finely graded, like you can see in the lower picture. It's 2 micron diamond. We also work commonly with 4 micron and 8 micron. And you'll see the samples that are coming around, the panel that says CDC2. The 2 means 2 micron. It's smooth to the touch. Most people wouldn't even know it's plated. They just think it's a hard metal. The reason it's gray is because you do have diamond slightly sticking up above the surface, and it changes the reflectivity of the coating, similar to what I was saying before about Nickel-teflon in the question session before. Silicon carbide is more commonly used in the 1 to 5 micron size range for hardness and wear resistance. It's also possible, primarily with diamond, to use submicron diamond. And when you use smaller diamond, you get less of it in the coating. So instead of, for example, 30 to 40% diamond like you see in the picture there, or 20 to 25% silicon carbide, which is common like in the top photo, with submicron diamond, usually about 150 nanometers in size, you'll have about 10% in the coating. So why would you use less diamond? It's because it's smaller. It's because it's even smoother than the standard diamond coating. So if it's up against some sensitive material, it can be things in the paper industry, textile industry, it can be in cylinders if you've got seals, if you want the surface to be even smoother, that's an option that can be done. And thicknesses of these materials, of these coatings, typically 1/1000th of an inch is sort of a baseline. It's possible to go thinner. We prefer not to do less than maybe 2 to 3/10ths, and the reason is if you go so thin, you just have a monolayer of particles, and I think it's important that the coating should have at least a few layers of particles to be regenerative. That as anything wears out, you're revealing new diamond or silicon carbide in that case. And that's an important point about what is the wear mechanism to these coatings. Diamond particles do not wear down. They'll get pulled out over time. So the correct prescription of which coating for which application depends on the type of wear. Is it sliding wear? Is it abrasive? Is it erosive wear? And that can help determine which version of the diamond coating is going to be most useful, or silicon carbide or another material going into it. So on the low end, 2 to 3/10ths, most commonly 1/1000th of an inch. And on the high end, we have applications that we're doing on a routine basis, they're 10 mils thick. And frankly, I don't think it's necessary, but you give the customers what they ask for. And a lot of that is chrome replacement applications where it was previously done with hard chrome onto heavy-duty pump equipment, things in the mining industry, for example, and that's what the parts were made to accommodate for chrome. Perhaps it was made to accommodate 10 mils on certain edges and less in others, but instead of changing the drawings, they just say, well, put on 10 mils thick of the diamond coating. And it sounds inconvenient, but actually it's not in a plating shop, because you go through the pretreatment, you can put it into the tank, it can sit there all day long with just simple replenishment, and you can be doing other work in other tanks at the time. So it's just sort of sitting there, building up in time. Oh, I'm sorry, let me go back. The charts, so taberware, I consider taberware similar to what a lot of the conversation was yesterday about neutral salt spray. I don't think any one of us in the room has ever had a customer where the object of their parts is to go into a salt spray chamber. And I don't think anyone's ever had a customer who say, oh, would you coat these parts for us? We want to put them on a Tabor test. I mean, the Tabor test is educational. It provides some sort of baseline, but it's just a test. What really is more important is how things function in the real application, in the real world. But to look at the chart that's on the left with the taberware, you've got hardened steel and it's losing over 12 micrograms per 1,000 cycles. So the lower number, the better. Hard chrome, then solid tungsten carbide. That's not a composite with tungsten carbide, it's solid tungsten carbide. And the lower one, CDC, that's the composite diamond coating. So it's showing that a relative wear loss compared to those materials on a Tabor test. Now, if you look at the chart that's on the right, it's looking at just Electroless nickel coatings. So on the far right side, you've got straight Electroless nickel. Then Electroless nickel with silicon carbide, then Electroless nickel, this time with tungsten carbide particles, and then diamond. And so what is this showing? It's showing that adding particles to Electroless nickel can significantly help the Tabor wear index, and that diamond is truly, the best material for wear. It's not surprising, perhaps, because of the hardness of diamond, but I think a lot of it also goes to the grading of the diamond, the quality of diamond that exists, and the purity of it. And so it just generally works better in Electroless nickel, not just in the coating, but in the bath as well. One of the most important things for the process is that the particles are pure. A lot of times, people will say, oh, I guess you use scrap diamond. And we go through millions and millions of carats of diamond in our shop alone, plus, all the other shops that we're aware that are doing it. And people assume it's scrap diamond, and they'll say it to my face. I wish it was. It would be, even cheaper. And the way it is now, it's very economical because of the volume we use. But it can't be cheap scrap diamond. I don't know if you can really buy cheap scrap diamond, frankly, in the world. You can buy it from sources that aren't as pure. And the issue is, if there were impurities, the particles themselves would start to plate, they would snowball, it would cause problems in the coating, it would cause problems in the bath. Those things don't happen because of the grade diamond that's used, which makes it a reliable process. So some typical wear applications, I know it's a thought that shops especially are going to have. These are typical applications for hard wear resistant composite EN. And I won't read all of these off because these are industries as well as specific items. If you have anything in those industries where we can be of any assistance, let me know. If you have other ideas, let me know as well. We're also happy to help any shop get involved with composite EN just for the ability to offer your customers something new and give them the opportunity to try something. And it doesn't necessarily mean you have to put in the bath. If we can do prototypes for you, we want to grow the field even further and contribute in that way. So the next section, or the next type of composite electroless nickel, are related to the first. And it's because it uses hard particles. But now it's using hard particles that are large enough to actually cause friction. And for those of you who have seen the coating or about to, you'll see that the CDC is very smooth, the CDC2, but when there's the 20 and 40 micron versions that are also going around the room, it feels like a fine nail file, a fine sandpaper. We can get up to something that's analogous to sort of a coarse sandpaper as well. And these are very interesting and relatively new, especially in terms of the volume. They think they're the fastest growing field of composite electroless nickel now, and it's because of desire for more energy transfer in applications, to have friction shims between a turning device and then a mating device to be able to maximize the energy transfer from one to the next. We're coating components for everything from wind energy turbines to automotive to robotics to anything where you've got turning parts, and it's often much more efficient and economical as well as better performing to have a shim between two parts with one of these coatings sandwiched together, rather than taking an entire component and engineering one side or the other to then have that friction capability. And certainly, imagine taking a component and having to mask off everything except for one mating area. A shim is often the easiest way to go. So you can see in the photograph on the left side, that's what the surface looks like. And it's really the surface of any composite coating with diamond or some other material like that, where you've got the particles sticking up. That's what provides the characteristics for the frictional properties for the light reflection properties, and then the panel that's on the right side, that's similar to what's being passed around. That happens to be 40 micron diamond. We can go up to 100 microns in size, so anything between 20 and 100, that's typical for these frictional applications. It's even being used on things that go into the human body in medical and dental devices as well. I'd worked with diamond and electroless nickel for probably about 15 years before I even learned that, aside from being the hardest material known to man, that diamond is also the best conductor of heat energy of material, a common material like that. So we then did experiments with a university in New Jersey to test, well, will the heat transfer properties of diamond translate to use when incorporated into electroless nickel? And what this chart is showing is the heat transfer rate of a tube with both either hot or cold liquids put into the tube, and measuring the rate of change of temperature, both getting hotter or colder depending which direction we're going, from bare aluminum tubes on the left side to aluminum tubes, the exact same ones with electroless nickel, aluminum tubes that were either blasted and tested alone to give it a rougher surface, or electroless nickel plated and blasted, or the composite diamond coating. And what this is showing is the rate of heat transfer is genuinely improved by the presence of the diamond, that it's not just the nickel and it's not just the surface, which may help with some convection heat transfer as opposed to the other method of heat transfer that can be done through the material alone. So this is something that is not as widely exploited as composite diamond coatings for hardness and wear resistance and frictional properties, but there's a lot of opportunity here, especially for things like I mentioned on the screen, heat sinks in electronic applications, aerospace applications, especially things that are being done in a vacuum, ways to draw heat away from a material or a device to not cause damage to it, and automotive as well. This one often gets the most interest from people. It's not nearly as common as the diamond coatings and the low friction coatings that I'll get into either, but just like you can put in bone or you can put in intumescent materials or anything else for that matter, there's certain materials that are forensic, certain materials that have unique identification properties to it, and we can put that into electroless nickel. And actually we've been involved in putting into other coatings, electroplated coatings, other metal coatings, powder coatings, paints, and things like that. But let me explain the pictures first. The two, it's not two actually bolts, it's one bolt. In the top picture is under normal light, like fluorescent LED light. The bottom picture is turning off that light and turning on a black light, and you can see the coating glow at you. Normal electroless nickel certainly wouldn't do it. The bolt itself, whether that was steel or stainless steel, wouldn't do it. It's because these particles are in there, they're throughout the coating, they're sticking above the surface, and they are reacting to the UV light and glowing a color. And why would you want to do that aside from making some cool pictures to talk about in Indianapolis? The reason you'd want to do it is you want to see if something's authentic. There's year after year growing need to identify if products are authentic. And that can be everything from high-end luxury goods to aircraft parts. And in this day and age of CNC machining, 3D printing, it is very easy to make a component for everything from cars to aircraft to even body armor, which gets counterfeited, which is unbelievable. There's people in the world, and I know I'm going off on a little bit of a tangent here, there's people that would make counterfeit body armor that is meant to protect people, but it is done, and it needs to be able to be identified as authentic or not. A coating like this, people can make something in a CNC, they can make something in a 3D printer. Let's see them put electroless nickel with identification particles into it. So it's one higher level of protection of identity of either consumer products or industrial parts, and it can even be done with different colors, and it can be done with invisible means, where if you shine a light on it, you won't notice anything, even if they know to look for it. But with a detector, like you see in the picture, the red and black thing that's about the size of a remote control, that can be held up to one of these coatings, and it will tell you if it's authentic or not. And not only does it say authentic or not, but it can be programmed to react with certain types of materials, because there's about 30 different ones that we can use that we know of so far, and the detector can say if it has material 1, 2, 3, 4, and so on, or even combinations. So you can literally embed a lot code or a manufacturing code within a coating into Electroless nickel, which happens to be very versatile to do it. You can do that for authentication. You can also do it for wear identification. So imagine this bolt. Imagine it's some critical component. Maybe it's a mold for an automotive application that costs $500,000 or more. You put this coating onto it. You shine a light on it, you're going to see it. Then you put whatever on top, Electroless nickel, chrome, any functional coating. You shine a light on it, you won't see anything. But with periodic inspection of that mold, and that's just one example of where this is useful, as soon as you see the color emerge from the surface, it means you've worn through the functional layer and you revealed the underlayer. And that's saying, take me off the line, strip me and recoat me before you wear into a mold that then has to be rebuilt, or pump, or anything. We've done things for nuclear power plants with a coating like this, just to avoid wear into the base metal. And if it happens to be a molding application, to not making things that are out of specification. And as a mold wears down, it's going to have less gloss, it's going to be using up more plastics that are going into it, increases the weight of the vehicle. So there's a lot of reasons, obviously, why you want to know when you've worn through a functional coating before you get into the base metal. So this is a interesting technology that can be helpful in applications like that. Now let me talk about low friction, which up there with wear resistance is probably the most common one, and it's been spoken about very well already at the conference here. I'm going to start with an alternative to Nickel-teflon, because then I want to spend a lot of time talking about Nickel-teflon from a slightly different perspective than what's been presented so far. Nickel boron nitride was developed decades ago and is a very, very interesting and useful coating. And it wasn't just, it didn't come out of nowhere. It was developed in conjunction with trials with graphite, moly disulfide, all sorts of other lubricating materials. And this truly proved to be the best material in terms of consistency and properties. It is something that can replace Nickel-teflon, but it's not exactly a direct replacement. There's certain areas where it's superior, certain areas where it may be inferior. And I think the most important part about it is Teflon is a relatively soft material. You put it into Electroless nickel, and as you saw in Helmut's numbers, it brings the hardness of the Electroless nickel down. When you put boron nitride in, which is a ceramic particle, it does not reduce the hardness of it. So why does that matter for a low friction coating? I often use my hand as an example, that if I'm rubbing a surface with my hand like this, there's low friction. But if I push hard, because my hand is soft, the friction goes up. If I do it with the back of my hand, that's harder with the knuckles, the friction doesn't go up just because I'm pushing harder. It's the same way with these two coatings. With Nickel-teflon, as good as it is in so many applications, under high loading, high pressure, the coefficient of friction will go up. With the boron nitride version, the coefficient of friction does not go up the same way. In fact, we have charts where it even slightly goes down, because whatever the mating material is, it's up against the particles sticking above the surface. So there's a lot of applications where it's useful. It is harder, it's more wear resistant by itself, but it's also typically applied at a thicker layer thickness, because it has a full plating rate, meaning 0.8 to a mil per hour, just like normal mid-phos. It can be done in low, mid, or high. It's typically in medium phosphorus. So with that plating rate, it's more common to just plate this 0.5 mil to a mil thick. And it's actually also easier to operate from a plater's perspective because the boron nitride particles, they don't need the same level of surfactants and wetting agents to get them into the bath. PTFE particles don't wet. Ceramic particles, diamond particles, and so on, they do wet. So there's a lot of nuanced surfactants that are put into the dispersion of the particles so that they'll work properly in the bath for consistency, for optimal performance of the bath, but it's less, and therefore it's not stabilizing the bath the way Nickel-teflon systems do. So you're getting a much faster rate. You also get a full bath life, 10 to 12 turnovers from a boron nitride bath, as opposed to the much lower numbers with Teflon, again, because you're not adding all of those wetting agents and surfactants to it. And at the end of a bath life, the boron nitride, just like diamond or silicon carbide, can be removed from the bath, cleaned, rejuvenated, and put into the next bath. So it's expensive to start up a boron nitride bath, but it's an investment because you can then keep reusing the particles. The only particles you're using is what actually goes into the coating, and that's part of the mil square foot cost, which, going back to my comments yesterday, that's the mil square foot cost of the chemistry, which is a small portion of the overall operating cost to run this or any other process. So be happy to talk to anybody anymore about that or other alternatives. But Nickel-teflon is worldwide and a very important and useful coating, fortunately. I think it's the most widely commercialized composite and has been historically much more complicated, even though there was more leeway in terms of what materials were used for it. Typically, 20 to 25% Teflon, 0.2 microns. The typical thickness is anywhere from less than a tenth to a mil in thickness. And we talked about the color before and how it's very identifiable. Used in so many applications, it's really countless. I want to talk more about the process of doing it, since in this conference a lot more has already been said about what the coating is and how it works. But to give an idea of the process, as I said, the particles don't wet. And so the way you get them into a water-based plating bath is very intense mixing with specialty surfactants that encapsulate the particles. Now, when you could use longer chain PFAS chemicals as in the past, the job was a little bit easier because it would encapsulate the particles. The newer versions don't have that, but it's still doing the same thing, surrounding the particles essentially so they can be introduced into the bath. And that's great, but it then does require the bath to be operated a certain way, and that is to not de-wet the particles, to not shear off the surfactants from the surface of the particles, and that can be done relatively easy with the wrong kind of pumps that have high shear that we typically use day in and day out on straight EN with diamond or other hard particles. They would take the particles of Teflon and shear away the wetting agents. The Teflon will then float to the top of the bath, and the bath will still have all the surfactants inside. So, because it's sensitive to that kind of agitation, a simple mixing device like this is preferred, and it's actually something that you can just stick in the side of the tank, preferably towards the heater, because localized heat is also not good for the stability of these baths. And so once you have a simple but proper setup, you can get very, very reliable results for it. And I think that's one of the, I guess, misconceptions about it. Even though it's a more advanced bath, it's run in a simpler way. And to make the apparatus simpler actually performs best over time. The mixing is actually generally done 24/7, even when you're not using the bath, when it's been cooled, just to keep everything, in dispersion in the bath, and not a big deal to do that. Standard pretreatment, Some shops will do a Electroless nickel strike before the Nickel-teflon. Some shops don't, personal preference. I think a lot of times it depends what the base metal is, and if it's aluminum, they don't want to bring zincate into the Teflon bath. But either way, a lot of shops will do one or the other. One thing that's important to know, unlike the particles I've discussed so far, the PTFE particles are irretrievable. You can't get them out of the bath. I mean, you could, but you couldn't reuse them. So if it's going into a waste stream where you can't have the particles, you'd want to remove them, but you're not going to remove them, clean them, and reuse them into the next bath, which means that the performance of the bath, the lifetime of it, is particularly important because, as a rough rule of thumb, when you make up a Nickel-teflon bath, about half the cost is the Teflon, about half the cost is the bath itself. I want to talk about how the baths work, and especially about recent improvements to the process. And some of it ties in things that I've said already, things that other people have said. I'm going to use a term that I spoke about at Surfin, 2022 Nickel-teflon. It's not any trade name, doesn't mean anything. It's because the year 2022. And what I want to just differentiate is the baths that are available now in 2022 compared to what may have been available 5 years ago. And I'm not talking about any one company, because fortunately there's multiple companies that are selling things that I would say fall under the 2022 Nickel-teflon technology. And I think an important message that I'd like to share to any shop that's doing Nickel-teflon now or considering doing it, well, if you're doing it now and you're using a process that's more than a few years old, I think you should talk to your supplier about a new process, because there are significant differences now than what was available. And I know, as other people have said, no one wants to change, but in this case, you can change for superior performance, better environmental reasons, and I'll go through all of those. So 2022 Nickel-teflon is better now than it has been in the past for performance, ease of use, cost, health, safety, environmental, and regulatory. So, you know, it's pretty impressive that you can make all of those areas better, even as there's more restrictions on what materials can be used to make these systems work. So in terms of performance, these are some of the key areas that are better in more modern systems. And one is plating rate. Historically, it's been about 7.5 to 10 microns per hour, but now there's systems that plate 15 microns per hour. So it's a significant improvement in plating rate. You know what that means, obviously: more throughput, higher profitability, lower overhead labor and energy costs. So this is a significant improvement in more modern, what I'm calling 2022 baths. Also, the life of the bath. And again, very important, because it's always important. It's important in this day and age when we're trying to save costs on things like the nickel sulfate, sodium hypophosphate. When you've got a bath with Teflon that's irretrievable, you really want the bath to go longer. Historically, a benchmark is about 3 turnovers, though in commercial practice, a lot of companies are getting 1 to 2 turnovers on the bath. Now there's systems that routinely are going 4 to 6 turnovers. So it's a way of literally cutting your waste treatment costs in half, not to mention downtime by changing baths. And one of the other things important, I think, to know in terms of downtime is, because these baths are so much more stable than straight Electroless nickel, because of the addition of the wetting agents that are in there, you don't have plate out problems onto the tank. You don't need to pump out the bath periodically, everything from what I've heard daily to weekly, in different presentations. You don't need to do that, which means that you can leave a bath in for all 4 to 6 turnovers, run it, and then just switch it. The coatings are also much more consistent now in terms of quality, in terms of the color that we talked about in the last session, in terms of that Teflon smut being consistent. And I think also because when it's done in some situations, some of the 2022 systems are single components. You don't have that violent pH reaction like you see in this photo. what I mentioned before about agitation, to not have hot spots at the heater because localized heat will hurt the Teflon dispersion in the bath. What you're doing right there, that happens to be just straight EN, not Teflon in the bath, but that's destructive to the Teflon in the bath, having that kind of pH reaction. So if you're using a component that has a pH more compatible with the bath, you don't get that reaction, you don't get dissociation of it. Ease of use also, starting with the dispersions themselves, the stability of them has actually improved in more modern versions compared to what people used in years past, with a longer shelf life, even greater resistance to freezing and hot and cold storage. We've even found some dispersions you can freeze it solid, just let it thaw, shake it, and reuse it. So some of them are actually more forgiving. And then going to what I was saying yesterday, but now tied into composites and Nickel-Teflon specifically, the single component EM baths are saving on labor, making it easier to use, higher quality and consistency, and that's because the bath is always in balance, because of the pH compatibility, because the A component is normally not complex nickel going into the bath. With a single component, it's a friendlier way to replenish the bath and leads to more consistent quality, but ease of use as well, which is this advance that I'm highlighting. Now, the opportunity to use replenishment pumps to keep the bath at a consistent level, and no need for auxiliary wetters. You don't need extra wetting solutions to add to the bath over time typically. There's some applications where some shops will still use that. For the vast majority will use a bath and a dispersion and no other auxiliary solutions, which makes it a lot easier to use compared to systems of the past. Cost benefits, obviously a very important consideration, and these have been achieved with the 2022 Nickel-Teflon for all the reasons that we've discussed somewhat over the conference. Time to wrap it up?
Please.
Okay.
So we have room for the others.
Thank you. Low metal operation. It's more practical with Nickel-Teflon than it is with just Electroless nickel, and that's because of the slower plating rate inherent in Nickel-Teflon. And so it's a good opportunity to do a low metal operation, and also is good for the environment to have low environmental. And I'll really end on that because we've talked about the environmental advances to this, and just, this coating that can reduce friction, can reduce energy consumption, is above and beyond what all Electroless nickel is. I think it behooves us all to realize all Electroless nickel is green. All of Electroless nickel is done to protect parts, to avoid corrosion, to make things last longer, to avoid energy use, and so on. So this is one more way with composites, whether it's Teflon or the hard particles, to produce that. So sorry I went over. I should have been watching my watch, but I appreciate everyone's time.